detecting and labeling cracks in pharmaceutical tablets when other methods fail, taking complex materials imaged by micro-CT and providing full and automatic material image segmentation, taking noisy electron micrographs and denoising them so that you can do a full and automatic segmentation of the cellular architecture, all delivered by one platform. That's deep learning, but it can even restore high-resolution details from low-resolution images with super-resolution methods. How can one technology, deep learning, provide all of these answers for scientific imaging? That is the topic of today's daily. Stay tuned as we demystify deep learning for imaging scientists. Hello and welcome back to the Dragonfly Daily. This is your daily source for fresh content on tackling the challenges of scientific imaging with, as always, your host, Mike Marsh, the product manager of Dragonfly. You can follow me at Dragonfly Wizard on Twitter. You can also connect with me on LinkedIn or follow me on ResearchGate. And as always, I do encourage you to check out our YouTube channel where you can find our fresh content coming out daily, but all of our other videos and useful tutorials, not only on just image processing, but using Dragonfly. Now, today's lesson 15, is deep learning for imaging scientists. If you are watching on YouTube, find that subscribe button and make it gray. Also, please give us likes. We need likes on this video series so we know you want more content on deep learning. Please, I'm looking for 500 likes on this video so that I can tell my boss I can keep doing these videos. Now, the deep learning lesson plan. This lesson, Deep Learning for Imaging Scientists, will give you the background information you need to comprehend and understand the following live demos that will come later in the week. Lessons 16 through 19, we will look at denoising applications, we'll look at image segmentation, we'll look at super resolution, and then in lesson 19, we'll cover some advanced topics such as transfer learning, object detection, and more. Now, this lesson 15, Deep Learning for Imaging Scientists. At this point, I would normally tell you this is going to use Dragonfly 4.1, but this is an exception. Not today. We're not actually going to do any live demos. This material is of general use for anyone who wants to learn about deep learning. So whether you're using Dragonfly, some other platform, or whether you're writing the code directly in TensorFlow or Caffe or PyTorch, it doesn't matter. This is going to teach you what you need to understand about deep learning. Now, deep learning is everywhere. We understand this. We see it in the popular media. We see it in the literature. When I talk to Alexa and I ask her what time my flight is tomorrow, she's using deep learning to decode my voice. When you have self-driving cars, they're detecting where the pedestrians are, where the bicyclists are. You have tabular data interpretation where you can detect breast cancer risk in patients better than other methods. You even have tools where the computer can read films better than leading radiologists. You also have crazy things like this video of Obama, but it's not really Obama. It's completely synthesized by deep learning. So deep learning is everywhere and it's solving problems, it's creating deep fakes, but what is it doing? We will not talk about any of these applications. Instead, we'll talk about deep learning for scientific image processing. Now, let's start talking about image processing. We can think about image processing in different ways. I want you to consider an image filter that takes a noisy electron micrograph like this and turns it into a less noisy image. Image filters you can think of as transforms. This is transforming a noisy image into a less noisy image. Likewise, you can think of image segmentation. Here I have a ceramic matrix composite, and I want to know what are the different material phases. Where is the exterior barrier coating? Where are the silicon carbide fibers, or the silicon carbide matrix, or the pores? All of that is really a transform. We're transforming one input image into another image. So what I want you to do is I want you to think of these image processing operations not only as transforms, but let's consider them as functions. We're doing a function to take an input and transform it into an output. Maybe we can use fitting tools to fit functions to our data. This would be the same way we fit a line to scatter data. If you consider the problem of linear regression, you observe some sort of XY scatter and you think Y is dependent upon X. You observe scatter and then you try and fit a function, in this case a line, a simple Y equals mx plus b. You try and fit that line to the data. In this case, a line, it has two coefficients that must be fit, or two parameters, the slope and the intercept. I can create a number of different candidate lines and I can evaluate, is this a good fit or a bad fit? In order to evaluate a fit, I have to have some sort of cost function. In this case, it's the residual. For all of my observed data, how far is the predicted data, the blue line? And so if I keep changing my slope and my intercept until I have a very low residual or a very low cost function, that means I have a good fit. And that's what we're trying to do when we're trying to fit a function to data. So the optimizer here is really about finding a good fit. Now, if we're looking at image processing, this is not scatter data, it's image data. So the question we must ask is, what function will we use to fit to our data? What is the cost function for deciding when it's a good fit or not a good fit? And then what are the coefficients we must fit? Now, in terms of this question, what is the cost or what is the function we're trying to fit? We're going to use a construct called neural networks. Now, Before we get to neural networks, I want to put deep learning in context. So we hear a lot in the literature about artificial intelligence methods. Sometimes people don't use these terms precisely, but there is a very precise term. You'll find this Venn diagram all over the internet. This one comes from NVIDIA. And what we're looking at here is there are methods of things we call artificial intelligence, different algorithms. So if I play chess or checkers against the computer, it may feel like I'm battling some intelligent entity. Then within the whole scope of artificial intelligence, there are algorithms, mostly mathematical models, called machine learning. Now, machine learning are these tools where when you provide them more examples, their performance get better. So there are many different types of machine learning, and they do things like when we have examples of what is spam, they can identify in future tests what is spam and help us. Now, there's a special case of machine learning using something called artificial neural networks, and that is where we will learn about deep learning. So what you want to know here is that deep learning is just one type of machine learning, and sometimes you can collectively describe all of these as artificial intelligence. Now, why are we talking about deep learning or artificial neural networks instead of just other machine learning? So there are many limitations and caveats to this simple abstract plot, but I want to give you the idea that when you use other machine learning techniques, you may get pretty good performance with limited training data, but you'll often find that you hit some sort of barrier, some sort of asymptote where you're not able to continue to get better performance. With deep learning, we find that if you have a deep enough neural network model, a deep enough network, you can keep throwing more training data at it and get better performance. So that's why we like deep learning. Now, I keep talking about neural networks, but I haven't told you what a neural network is. In order to understand neural networks, we start with the idea of a neural neuron. That is the simple neuron, which this artificial neuron is sometimes called the perceptron. In this case, let's consider this mathematical construct where we're trying to evaluate some mathematical function, which might be a summation. Now, consider I have a table. I've gone around the neighborhood and I've made measurements on animals, and I've measured how tall is each animal? Does it sit when I tell it to? Does it ignore me completely? Does it sleep all day? If I have tabular data, maybe I would like some sort of, and I also make observations for each one of these. Is it a cat or a dog? Maybe I would like to build a function that can tell me is it a cat or a dog from those input data. Now, here, the way this mathematical function works is it takes all of these values, it applies some sort of weighting function to those, it executes a function, in this case a sum, and then it processes that function. It could just process it linearly, or it could use this sigmoidal function. There are newer functions that are really making deep learning networks turn off called the linear rectifier. So there are different functions here, and then we can take the output of that and we can scale this in such a way that maybe given all the input data, it will come close to 1 if it's a cat and close to 0 if it's a dog. So we can use this simple mathematical construct to make predictions. So this is great for linearly separable problems, and which is the case sometimes for is it a cat or is it a dog, but it might not be so great for more complicated tasks. We can map multi-output tasks onto the same structure. So now consider I have a table, my table is furniture, and for each piece of furniture, I know its height and its width. And so some of them are tables and some of them are desks and some of them are beds and some of them are chairs. So in this case, what I could do is I could construct 3 perceptrons or 3 neurons, one that is a bed neuron that looks at the height and the width of the furniture and tries to guess is it a bed. Similarly, a neuron for tables and similarly a neuron for chairs. Then I could take whichever neuron scores the highest and maybe that could be the output of my network in this case. So it's 3 neurons, but it's only 1 layer. This is called the single layer perceptron. Now, what if I want to take a more complicated problem like image analysis or image processing or character recognition? How can we map that onto perceptrons? Well, in the case of our animal data, we had 5 or 6 variables. In the case of our tables and chairs and furniture, we only had 2 values. Let's consider an image as a multi-input or a vector input. In this case, we have all of these pixel data where we have the brightness at every pixel. So if it's 28 pixels wide by 28 pixels tall, then we have 784 inputs. So instead of just 3 or 4, we have 784. Now, if I take the same architecture and I line up all 784 inputs and I create 10 neurons, 0 through 9, trying to say, given all these brightnesses and intensities at all these different inputs, can I tell you is it a 1 or a 2 or a 9, etc.? The answer is no. This simple single layer perceptron really has no predictive power. So there are limitations to the single layer perceptron. However, we can make our networks more advanced. If you take that output layer of neurons that's predicting is it a 1 or is it a 2, and you take that input layer of neurons that tell you all of the signals from the 784 pixels, you can insert a layer in between. If you have one of these layers, these are called hidden layers. If you have one or more hidden layers, that's when we're talking about deep learning. So one or more hidden layers is the hallmark of deep learning. This is also sometimes called the feed-forward network or the multi-layer perceptron. Let's return to this image where we're trying to solve, is it a 9 or is it a 2 or what number is it? Now, before I go any further, I do want to let you know that the next several slides, they're really taken from a terrific YouTube series on neural networks. This is a YouTube series done by Grant Sanderson on his YouTube channel, 3 Blue, 1 Brown. I highly encourage you to check it out. I'm going to summarize some things in 4 or 5 minutes, but you can get a really detailed dive and understanding of this if you want to sit and listen through some of Grant's lectures. So, and I will link to that in the YouTube description below. Now back to this problem. So we have all of these pixels and we want to try and construct a multi-layer network that can decode and tell it, is it a 1, is it a 2, etc. Now, in Grant's example, he posits the following network. So we'll have 10 neurons on the output layer, we'll have 784 input signals on the input layer, and just almost as a contrived example, it doesn't even have to be this, but for this example, we will insert 2 hidden layers, and we'll describe why in a few minutes. 2 hidden layers, each of 16 neurons. What you will have is you'll have all of these perceptrons, these functions that will take 784 inputs, they'll evaluate a function and then pass on a signal to the next layer of neurons, which will evaluate all of the input from that previous layer of 16 neurons, and then they pass the signal on to the final layer of 10 neurons, each which comes up with a score of is it a 1, is it a 2, etc. So in this case, we have all of these weights in this network. We also have something called biases. We'll look at that in just a minute. So we have 13,000 coefficients in this network, much more complicated than simply fitting a line to a function. Now, each one of these neurons in the first layer, as I say, it's fully connected to the 784 inputs in the 784 inputs from our pixel data. So you have some sort of function, which could be linear, or it could be a linear rectifier, or it could be a sigmoid. Then you have all of the weights, and then you may have sort of a threshold for activation, sort of a bias or an offset to help decide if that neuron should be more or less sensitive to the inputs. So many parameters when you count all of those weights and all of those biases. So the question is, what can we put in this neural network for all of those weights and biases so that it can have predictive value? How does the network get the proper encoding, or how do you optimize all of those coefficients? So this is what we call learning. We will have the algorithm see examples of data and learn when it gets wrong, learn when it's making correct, and to reward and positively encourage the network to find better weights and biases that give it more predictive power. Now, we can consider an initialization. So if we consider that network and we don't know how to start, so we just randomize all the weights and biases in the network. If you just randomize it, it's going to be a garbage network. You can expect that if you put data in, it's going to give bad results out. So if we put randomized weights into the network and then we put in an image of the number 3. Now, if you look at the output of those 10 neurons, you can see it got a pretty high score for 3, but it got an even higher score for 8. It says it really thinks it's not a 5. This is all random because of the randomization of the weights. But what we can do is we can evaluate how bad is this current prediction, how bad or good. Now, when we looked at the simply fitting a line to our data, we only had 2 coefficients to change, but we also had a scoring function or a cost function, which was the residuals. Here, our cost function can be simply defined. What we'll do is we'll take the difference between what the output should be and what the output is. So let's consider the output would be 0 if I think it's not a number, and 1 if I think it is a number. So if it's 1 or 0, we can take the difference of how far away was the prediction. So in this case, it gave us 0.88 instead of 1.0. We can take that difference and we can square it. We can sum that over the entire last layer of neurons and we have a score. So as this score gets more and more correct, that is, as the score gets closer and closer to 0, it means the network is making a good prediction. Because if this predicted a 3 with 100% and everything else with 0%, then our loss function would be 0. That means we can evaluate this cost function and then we can put another number in. So we evaluate the cost function and then we want to do some optimization. So because we know that everything that was feeding into this 3 neuron, if it was doing a good job and there are weights we can choose to make this get a higher number, we can specifically add weights to those connections and we can reduce the weights on other connections. So the back propagation is saying, where is the error? and then which neurons are contributing to that error and which neurons are contributing to success. So by analyzing this, the optimization function actually tunes the network. Then you present another number and you observe the output or the cost function, and you continue to iterate. You present more and more examples, and the network gets better and better as the weights start to converge. Now, let's return to this example. We should pose the question, and Grant does this very thoroughly in his YouTube tutorial series. We should pose the question is, why would we even expect a network of this architecture to work? Well, there's a very reasonable way if you understand how the visual cortex works. You could suppose that you have a neuron that's useful for recognizing zeros and one that's recognizing nines. Now, you might suppose that that neuron works like this. The 9 neuron knows that it should find a loop feature, and it should find, or say, a loop pattern and a line pattern. And so whenever these patterns exist in sequence, then maybe we should consider that that is a 9. And then you would ask the question, how does a loop feature, or how is a loop pattern recognized? Well, you consider the loop pattern could just be composed of different little line segments that are detected upstream. So you could have features that are aggregated into patterns, patterns that are then aggregated into numbers. And so we can extend this idea to our network architecture. So we could suppose that these neurons in the beginning detect features such as the little line segments. These detect loops and lines. So these patterns are then fired, and then if a 9 is getting a strong, or sorry, if this loop pattern is giving a strong signal and this line pattern is giving a long signal, then the 9 neuron knows it should fire. So all that could be cascaded and built into these weights. Now, this is a thought exercise of what the network could look like. Now, we can go in and look at all of these neurons and see, are there neurons in the first layer that actually detect these little features? Are there neurons in the second layer that detect these patterns from these features? Now, it turns out this is not what happens. If we look at the neurons in the first layer, we see that the features are not little line segments, but this complicated basis set. Now, this is interesting in many ways. So it turns out that the network doesn't have to work the same way our minds work in order to be successful. Instead of having a basis set of little bitty line segments, it has this seemingly arbitrary basis set. But it turns out there are practically an infinite combinations of basis sets that would be useful in adding up to detect patterns that can then be used to add up to detect numbers. So it doesn't converge where we think it might, but it is still successful. Now, if we consider this, it turns out that how successful this network is, it actually achieves around 97% accuracy. But there is a way we can improve the network. If we borrow from that biological model where we know that that first layer, or one of the early layers in our biological neural network in our visual cortex, is actually looking at little line segments and looking at shadows and looking at other features, we can insert a layer in our neural network model before this first hidden layer, specifically designed for convolutional kernels. These convolutional kernels will then become very good at picking up little line segment type features that can be aggregated in patterns. If you do that, if you insert this layer of convolutional kernels, you're now using something called a convolutional neural network, and your accuracy shoots up very close to 100%. So convolutional neural networks are a class of tools where you're using a convolutional filter layer at the beginning of your network. And these are used throughout deep learning for visual detection and processing. So we've been talking about identifying number 0, number 1, number 2. If you want to move from that onto a topic such as image segmentation, it turns out we're no longer trying to detect a number, but we're trying to process the image. So our image transform here is not just identifying is it a 1 or is it a 2, but we take an image of grayscale pixels and we return as our output an image of segmented pixels. So we label which pixels are voids and which pixels are matrix, etc. So in that case, you're not outputting a layer of 10 neurons, but you're outputting a whole image of neurons, or as we'll see in later lessons, a whole patch of neurons. So a patch of unprocessed pixels as input and a patch of segmented pixels as output. Now, this whole idea was first described in a paper by workers at University of Freiburg, which introduced the idea of the UNet, or a specific network architecture that allows you to look for these patterns and then identify those patterns and then generate outputs of the same shape. And that's how we were able to do segmentation. This is done with an architecture that's sometimes called autoencoder. You may find that in some tutorials in the literature and on the internet. Now let's consider using this UNet architecture on an image sample. What we're looking at here is a micro CT image of a denim fabric, and we have area that is just air, and we have area that are small fibers and big fibers, and we would like to segment these. And so this is just a stack of images. You can think of it as a 3D volume or a stack of 2D images. Now if we take a stack of images that are unprocessed and a corresponding stack of images that are processed, in the example we show here we actually just use 6 slices of input data, and with the tools in Dragonfly it only takes us about 5 minutes to label these so that we have our labeled output. If you're able to pair the input images with the output images, you can use those to train a network. And at each stage, it knows what the output should look like, it knows the output it gets out of the network, and so it's able to evaluate a cost function and learn and improve. This is able to train on a modern graphics card or a modern GPU for actually running this training and updating the weights of the network. It only takes about 12 minutes, and it results in a trained UNet model. The UNet model is then able to take the full 3D stack of images and process it and label every pixel in every slice. Is it background air, or is it small fibers, or is it big fibers? And once you have that, then you can do all sorts of work in the computer, like you can digitally remove the big fibers and see what the small fibers look like on the inside. And so this is just eye candy, and this is just showing you that once you have processed the data, you can easily visualize and start to analyze and interrogate the internal structure. So I do want to make a mention here that the tools that we're showing and the discussion we've provided so far is based on a model of processing data on 2D slices, each slice at a time. Now, if you process a whole stack of slices, then you have a stack of processed slices, which is a 3D result. There are ways of doing this with 3D patches instead, and we actually introduced that in the next version of Dragonfly. But right now, all the work and discussion I'm showing is based on processing 2D stacks of images. All right, let's go to the next slide. Now, here we're looking at another example. Here is an image shared by Sydney Pesiornik at PUC in Rio. And here we have a micro CT slice of a pellet, an iron pellet that's basically ore from a mine. And in order to characterize these, you really want to understand not only where the pores are, but where the cracks are. The intensity is exactly the same, so a naive segmentation algorithm will fail. But deep learning is capable of building up patterns and learning to differentiate cracks from pores. Here's an even more complicated case of cracks. On the left, I have an unprocessed image, and on the right, I have the cracks predicted by the deep learning algorithm. And so when you extrapolate and you look, not extrapolate, but when you process in all those slices, you're able to see where the cracks are. Here's a ceramic matrix composite that's been placed under tension and it forms cracks. Now we're able to visualize where those cracks are, what their geometry is, what their spacing is, what their angles are, and all that can be done after you've done this segmentation. Here's an example from a bio-SEM. So here we're looking at SEM image as a plastic embedded stained tissue sample. In this case, they're rat neurons. This comes from Angel Paredes at the FDA, and you can see how complicated the image is. If we're interested in understanding where the cell body is, where it is different from all these processes that are exterior, you may want to segment the mitochondria separated from the rest of the cytoplasm, and then segment the nuclei. And here you can see what it looks like close up. So this is the result of training a neural network on a number of examples of manually segmented images where it's able to learn. There are a number of different applications, not just segmentation. You can also do denoising, you can do super resolution, and there are different neural network models for doing all of that. So here are a list of some of the network models that we found in the literature and re-implemented in Dragonfly. If you want to use our tools, you can read the literature and re-implement your own models. You have everything you need in our toolkit to re-implement your own neural network models. So the ones that are not bold, we've been using those for image segmentation. The ones that are in bold, we've been using those for super resolution or object detection. So this is a look at the UNet model that we showed earlier from the workers at Freiburg. This is a schematic or a representation of FusionNet, which was a very useful model advanced a few years ago for segmenting neurons. So in all these cases, we're looking at useful neural network models for processing your data. So thank you for your attention. We will take some questions and answers. I just want to remind you, but tune into YouTube. If you're not watching live, tune into YouTube for lessons 16, 17, 18, so you can learn more about applications for Dragonfly, 16, 17, 18, and 19. So with that, I will take questions and answers, and I thank you for your attention today. All right. So let's look at the questions in order. So we did have a question at the beginning of the hour. Can deep learning be used for analyzing intact or possibly distorted bone? So you can use it for labeling bone from background, from soft tissue, or from hair. You can also use it for segmenting cortical bone from trabecular bone. It doesn't matter if the bones are distorted or not. It should be just fine. Let's see. We have another question. Yes, lost video. Sorry about all of that. Are we still doing training only on 2D layers? That's a great question. So in Dragonfly 4.1 and all the versions before that, all of the default models implemented a training and an inference, that is training and then applying on 2D slices at a time. So if you wanted to process a 3D stack, you would train a model and then you would process it one slice at a time, and then the results of all those slices stacked together would give you a 3D result. Starting with Dragonfly 2020.1, you are able to train 3D neural networks. So you can have slices of data where you're looking at data from that slice, but from adjoining slices or from slices slightly higher and slightly lower. You can have 3 slices or 5 slices, 9 slices. It doesn't matter. It does affect how much graphics memory is required to train and infer the model. So you do 3D modeling, and it can even be asymmetric. It doesn't have to be slice I and I minus 1 and I plus 1. You could have a model that uses slice I and I plus 1 plus 2. So I hope that answers that question. Now, the next question is, can the network separate densely packed nuclei into individual segmentation? So it all depends on the image. What I would say is, if you can look at the image and you can do a clean segmentation with your visual cortex and you can get the same answer every time, then we can train a neural network model with the same answer every time. Now, a lot of the times people are working with not only noisy data, but data that are low resolution. So if you have a pixel with partial volume effects and it's nucleus and cytoplasm, and maybe your nucleus is only 3 pixels wide and it's next to another nucleus that's only 3 pixels wide, you may be pushing the limit of what the deep learning can do. That's really because you're trying to get more out of the data than you're entitled to at that resolution. So I would say, if you can resolve it by eye and come up with reliable manual segmentation by a human, then a neural network will be able to produce training data. Next question: how do we feed 3D data set into a deep learning model? It's only in 2D slices. So I hope you understand the question I answered from Sydney should answer that. You are able, starting with the next build, to do 3D neural network models. In our case, in our case where you're using one of the older versions of Dragonfly, or even the current version, you are able to input the 3D model. It just processes it one slice at a time. So if you've got a stack of slices, it'll process slice 1, then slice 2, then slice 3, and give you a multi-slice output, which is the same as a 3D output. Okay, let's see what other questions we have. Okay, so Aya asks, how do you know what you see in super resolution treated images is true? Is there a way to evaluate how trustworthy it is without a ground truth? No, there's not. You can't do it without a ground truth. However, you can establish a ground truth when training data, and you can build test data sets. What I didn't talk about in today is how you do the training and how you use validation, but also how you can save back a test data set. So you can build a test data set. So you can scan a sample at low resolution and scan the same sample at high resolution in 2 or 3 different places. You can use one of those high resolution scans as training data. And during the training, some of it will be used for training, some of it will be used for validation. You can use the second area that you scanned as high resolution as a test set. So you can see how good does the predicted super resolution match up against the ground truth. So I wouldn't try and do super resolution without having a ground truth when you train the model. All right, next question. Let's see what we have. What are the publications on Dragonfly deep learning tools, its development and its effectiveness, etc.? So we do have a publication that's under review right now, describing the architecture and the general application of the solution. There are other people who have published with our methods in Dragonfly. They've done it with fiber analysis, and we have a collaborator at Merck that's published on the pharmaceutical tablets. So you can look to those papers. But if you want the peer-reviewed paper, you'll have to wait a little while longer. I think it's out in Material Science now. Next question: how many input images will it take to model? So it does vary. It turns out with our new architecture in 2020.1, we rely on something called data augmentation very heavily, and you can get by with very little training data. Certainly this process of training a neural network model and being able to use it, the bottleneck is how you prepare the training data. And we're using Dragonfly because we think we've made it possible to prepare training data very quickly. Now, I think we've gotten to the point where instead of spending hours doing training, now you can spend minutes, which is far better than spending weeks making a segmented data set. So we will cover that more on image segmentation tutorial lesson 17. Next question is, does 3D training require much higher GPU power and memory? Yes, it does. So when you do a multi-slice model, it has far more than those 22 million coefficients. You get 22 million times 3 or times 5. And that means you need more memory on the GPU, and each cycle of training requires more compute cycles. So it does take more compute resources for a 3D model. Now, another person asked, if you have a 1K by 1K by 1K data set, what GPU is required for machine learning training? Now, it turns out that when you build these models, you don't actually use the entire input image and the entire output image as your training data. You actually decompose the image into small patches. Depending on the patch size you choose, that will affect how much memory is required on the graphics card. So we'll look at some examples this week. We'll do some training. We'll see how some simple models, and it'll actually tell you how much GPU memory is required before you even start training. We have another question. Thanks for the great webinar. I'd like to know if I should expect any problems using a remote server in order to process the deep learning tools. Well, Dragonfly is not supported currently when you want to log in and do a remote session. I wouldn't say you would expect special problems related to the deep learning, but we could tackle that question offline in terms of what's the best way to use the remote resources. We do have a batch processing tool in Dragonfly that allows you to set up different trainings, and then you can set up those trainings to be dispatched to a GPU farm, so you could run those trainings on different remote machines, but that's not really covered in the scope of this week's webinar. The next question is, for four-dimensional CT data, the structure changes fast. Can the If you can hear me, I'll answer a few more questions. I'm sorry that you're having internet connection problems today. The whole video will be spliced together and produced on YouTube, so you can watch it here without interruption. Thank you again for your patience. There was a question on what is the lower limit on the number of slices of the data set. So if I have a data set of only 100 slices, but with sizes 1,000 by 1,000 pixels, will it result in overfitting since there are only a few slices available? No, that shouldn't be a problem. Again, it's not based on the number of slices or the number of pixels in each slice. It's based on a patch-wise framework. So what you'll end up doing is you'll end up processing the data in patches, and it's about how diverse your training set is in patches. So I don't think you'll get overfitting in that problem. Now, I had started to answer the question. I don't know if you heard my answer for 4D CT data, but yes, if you train it for one time step, you should expect that model to be predicted and give a high quality segmentation on the other data on the other time points. Now, the next question is, when will the new version of Dragonfly come out? Well, my team back in Montreal is working very hard to make that very soon. I'm expecting it to be sometime between April 30th and May 5th, but we don't know for certain. We want to make sure that it's a high quality production build that's ready for use. For those of you that want to try it in advance, we could make provisions for some beta testing. Now, the next question is, how do you report the accuracy or error or validity of neural network models? With linear models, there's R squared. Is there something similar? Yes, there is. So you can find this in the literature. We often use the dice coefficient, but there are other metrics you can use. And in Dragonfly, you can choose what metric. So I'll see if I can dive a little bit into the image segmentation method, but we won't be talking about that. I won't give you any specific today. Now, the next question is there a super resolution network in Dragonfly based on generalized adversarial network? We have not shipped one. We have built one, tried it. When you try and do super resolution using generalized adversarial networks, those networks can take a very long time to train. Now, I did talk with a colleague recently who was doing some work on this and able to network train just one day of training. So we should dig into this a little deeper, but we have implemented the models. We can share them with you. But in the past, the initial models we built, and this was some 1 to 1.5 years ago, they were quite slow because of the complexity of the network and the training process. Next question is, may I provide 2 references which Dragonfly? Oh, thank you. Sydney has a couple of papers, and he can show you where he's used Dragonfly for deep learning, and those are published peer-reviewed papers. Thank you so much, Sydney. You can either type it into the chat here, or if you send me the information, I'll include it as a slide at the beginning of tomorrow's webinar. That'd be terrific. Thank you so much. Okay. Now the next question is, can machine learning deal with inconsistent artifacts in CT data? Yes, it can, and we'll actually be giving a 1.5-hour webinar at an image processing workshop 1 week from Thursday to address that specific topic. And so I will be announcing that probably tomorrow. So we can talk about dealing with inconsistent artifacts in CT. Now there's another question. To separate touching objects when you have enough resolution, do you manually paint or separate the data set and then train the network? It depends on what you're trying to do. If you're just trying to label grains versus non-grains, then you have a binary segmentation, and that's what you train the model to do. If you're trying to segment a system where you want to identify the different grains and separate them, then that's an instance segmentation, which is a different challenge. There's a nice paper in, I think, 2017 called Deep Watershed, which shows how you can use deep learning neural network models to actually separate grains. We've implemented that in the lab. I think we may ship it with 2021, which is not quite sure. So it is deep learning does have the capacity to do that sort of problem. All right. Yes, it's true. I'm not sharing any video right now. I didn't want to overload my network, and there's nothing to see anyway. All right. So I think that answers all of the questions. The only question remaining is, what was the name of the paper? That you can Google Scholar. You can Google for Deep Watershed. I will try and put up that reference at the top of tomorrow's webinar. All right. Again, thank you so much for your patience. I hope you got something useful out of this webinar. It will be spliced together and put on YouTube for people that want to watch it later. Please share it with others. We look forward to having feedback. Engage us in the comments. We want lots of views. We want lots of comments so we know that people are getting something out of this sort of webinar series. So thank you again for your attention. Thank you for attending the Dragonfly Daily. I hope everyone stays healthy and happy. Take care, and we'll talk to you again tomorrow.